Okay, to start us out today, we're going to take a look at an ALEKS topic, one that is definitely more nasty than normal. We could go to class summary. And it's always an adventure in the system. Then under, let's see here, modules editors, this is where all of our problems live. And then finally, section 5.1. I believe 5.1 split across two. So there is 5.1a, 5.1b. And let me know if you can see that topic. I'll look as well.
Yeah, it says use a graph calculator. Yeah, that second one.
Right here. Gotcha. Use a graphing calculator. Oh, so that's why I missed that one. There's another one in 5.3 where we're going to see this again. And this is the one that I'm going to do in class as well. Using a graphing calculator to find an extreme of a polynomial. So let's try out this one right here. Using a graphing calculator to find intercepts and vertex. So if I saw this problem right here, you can use a graphing calculator. It's not terrible. It looks like a real graphing calculator. Let's try it this way, and then I'll show you an alternative method to get through this kind of question. So first thing we have to do if we're going to run through this is you'd have to hit the y equals button. We need to plot the actual polynomial given right here for f of x. So hit y equals. And I mean, it still looks like a real graphing calculator, but they didn't need to get this involved. They sure did, though. You need to click in one of these boxes. Just the very top box will do the job. Then type this out. And if you're using your ALEKS calculator, you probably find it easier to just type this out with an actual keyboard, like putting in your answer. Just hit X. To get an exponent, it'll be Shift 6, where you see the up arrow on your 6 key. Put in a 2 for our power 2. Right arrow takes you out of the exponent. Then plus 3x plus 4. Now we've got our full function thrown in, and to actually graph it, we'll hit this graph button right here. Does that make sense on getting the y1 function inside? Gotcha. Then hit graph, and there it is, but that's not necessarily going to help us find, well, it will help us find this. What would you say about x-intercepts based off this graph? Right, it's above the graph entirely, so hey, that's a freebie, that helps us out. Next thing we have to do is find the coordinates of the vertex. We want to round to the nearest hundredths. So we could just sort of guess, but that's not going to get us close enough. You need to hit the trace key. Once you hit the trace key, you can now move a point all the way to where it looks like it's at the very, very bottom. Let me see if I can zoom in on this whole screen. So get to the lowest point right about here. And now that x value, that y value, should be the values of our vertex. The trouble, though, is when I go to type it in, oh, actually, it didn't cause me any issues. Let me record it here. We have, for the vertex, x equals -1 point. We want the nearest hundredth. So for this one, we'll round up to negative, oh, I kind of missed, -1.56. So that gets our first one. For our y value, we'll say it's 1.75. That'll have to do the job. So that's what I put inside here, and we should be well on our way with this problem. Honestly, the worst thing again is using their graphing calculator. I mean, it's nice that it exists. It looks and acts like a real like TID3 or TID4, but it's still kind of tedious to use. Any questions about it so far? Okay, the other approach you can use is if you're solving this as an ALEKS problem, this will never be an actual real exam problem, I should say right away. In a real exam problem, we don't have a graphing calculator. So think of this as purely homework anytime one of these questions come up. So one way to do this is pull up your Desmos as an alternative application. You can type this in verbatim, f of x equals x squared plus 3x plus 4. And on Desmos, you can just click on that. And you know what? That might be the trouble with Desmos. I don't necessarily have the accuracy I want on this, right? I have negative 1.5. I did get to 1.75, that's helpful. But if I want more accuracy, let me make that happen in Desmos. I honestly don't know the answer to that question. Let me see if we can zoom in. Well, zooming in doesn't give us better accuracy. Let's see. As far as the options go on this, it looks like we're kind of stuck with our accuracy on this kind of problem. So you know what? The ALEKS calculator might be the better way to go for this type of problem. That's a bit unfortunate. Well, back in ALEKS, let's see how close we got to that. I'm going to type in negative 1.56. For the y value, it's going to be 1.75. Uh-oh, and they're not happy. Your answer is incorrect. Your vertex is incorrect. Oh dear. Let's take another look at that. Definitely not the funnest problem in the world. Yeah, go ahead.
It says a different way to do it actually on ALEKS. Is to hit the stream up, I think.
Oh, they're not using trace at all?
No.
Gotcha. Let's try this again. So y equals, I guess I have to retype that in, x squared plus 3x plus 4. Let's go to graph, and that must be this button right here for Extrema. So if I click on that, oh, we need to tell it where to find it.
So,
We can kind of move it around, right, to where we think it should be. And let's see if it can find it. It said x is negative 0.875 and y is 2.14. Wow, that's way different. Did we change the problem?
That's the max rate. Not the minimum. The bottom, it says underneath the find stream button, this is the minimum, that's the.
Oh, I gotcha. Dang it, that's really confusing. So I want to find the minimum, negative 1.5, 1.75. You know, that's what was making me nervous. That's what ALEKS told, or excuse me, Desmos told us.
Yeah.
They told us negative 1.5, 1.75. So I was thinking Desmos is no good because we wanted to the nearest hundredth, but I think it's should have been that. That's what they're going for on this. Let's give this a try, recheck. And they're happy with that. Kind of a brutal problem. Should we try it again just to see if we can run through a second one? Okay, kind of tedious, but if you all have to do it, we should see if we can get through it in class as well. Again, sorry for missing this one. I did see this in 5.3, so I was anticipating it, but totally missed this one in 5.1. So let's give it another try. Let's go. Let's find one that looks nastier. That's got a negative coefficient, so it's turning down. That might be a better one to try. So if you saw this, again, I'd probably just put it into Desmos and see what Desmos gets for us. But if you want to solve it the way they have it, thanks for the support on getting through this. Here's how we'll do it. Pull up your calculator, hit the y equals button. We're only going to plot one function, so you're just going to go to the very top where the cursor's flashing now. Let me zoom in a bit on this so we can see it a bit better. Type in this thing, your keyboard's a little bit faster, negative 4x squared plus 2x plus 4. Then hit graph. And my mistake was the trace button. That's absolutely not what we want on this. We need the Extrema. We can tell it where to look, so you can kind of move that around. Usually, I don't think you have to move it too much. Just make sure your maximum is between the vertical lines. That's where it's looking for maximums and minimums. Click Find Extrema. And my mistake is also, you're looking for the maximum on this one because it has a maximum. If we take the minimum, they're just finding the minimum in this range between the dashed lines. So it says we should have a 0.25, 4.25 on this one. So let's take a look at the instructions. Down to the nearest hundredth. So yeah, 0.25, 4.25 should do the job. So that's our vertex, 0.25, 4.25. Now we need intercepts. So I'm glad we did another one because finding the intercepts on this, you know, it's the same kind of thing, but we don't need extremas anymore. So I'll just click OK. And now I think this is a good time to use the trace button. We hit trace. We should be able to find a value right where x goes to 0. Maybe that's not the best way to do it. 0, it does that as well. Awesome. So Extrema and 0. Here, I'll move this one far to the right, this one to the left. Find our 0, and they found one of them. Let me click on cancel. Let's see if we can do that a little bit better. I'm going to zoom in on this. Click on 0, and I'm just going to move my strategy like this. I want to just find a 0 in that range. I notice Alex is not finding them all at once like I was expecting. You think this technology would work a little bit better. They could have over-programmed it if they wanted to. But no, it looks like it's just going to do one at a time. So my first inner 0 or x-intercept looks like it's at to the nearest hundredth, negative 0.78. Let's put that in, negative 0.78 on that one. We have to throw in a comma because we're expecting another one. So I'll click on cancel and let's do it again. 0. Now move this bound over here, this one over here. So now the vertical segments are capturing that location by the red dot where we're finding another 0. Click on find it and it says should be about 1.28. So let's put in a 1.28. And our hope of hopes is that should be accurate information. How does it look to folks? Does it look all right so far? Okay, kind of tedious and definitely apology worthy. Sorry about the tedious graphing calculator built into the ALEKS system. If we did it slightly different, let's just see how Desmos conflates with this. So redefine the function as f of x equals negative 4x squared plus 2x plus 4. Now we need better window on this thing. But if you kind of click around certain spots, it's telling us here, the maximum is at 0.25, 4.25. That's what we're finding right here. We also have an intercept, which looks like it's at about, I don't have an intercept until the second coordinate goes to a 0. Oh, I just need to go down there. That would be why. Here's my next intercept. So first is negative 0.781. We're more accurate than the calculator. And this one should be 1.281. Again, more accurate to the than the calculator we used. So actually we rounded those two. But at least we have the same exact values. So the graphing calculator, ALEKS, it takes a little bit of poking around and learning how to get going. You can come back to this video to see my mistakes and the help that we got in class to make it work. But Desmos is also just really, really fast at this. So it's probably the better environment if you're trying to avoid that tedium. But we should see if this is even right. So let me click the check button here. And yeah, they're happy with that. So that's what's happening with this one right here. Sorry about the graphing calculator. When it comes up, I'll always show how to use it and an alternative to Desmos for folks that would like to try it a different way. Any other questions or comments about this topic here? Okay, thanks for mentioning that. And again, just a standing thing about the class. If anything nasty ever happens in ALEKS, maybe the problem is really hard, or there's a sudden weird technology component like this calculator, never hesitate to mention it. I'm always very happy to discuss it. Well, back to our page right here. We're in section 5.1 on the last couple of examples. And I don't have a ton of announcements. Our quiz 6 is due today, and we should be getting through 5.1. That's our last couple examples in there. And in ALEKS, 5.2 is kind of a freebie. This is a really, really short section. Its whole goal is to set us up in 5.3. So that's where we're at so far. Well, we should be getting through these topics this week, but we'll see where we end up. Any questions at all, folks, about the announcements or other questions at the moment? Okay, let's jump into our current notes for the day. We're in section 5.1, and I have this on the Moodle webpage. I decided to take a screenshot since all these formulas in the purple boxes, they are all over the notes in this section. But if you want one spot with the 3 main takeaway points, they would be the vertex form of the parabola. We love when a parabola is written this way, a times x minus h squared plus k, because it automatically reveals the vertex, the highest or the lowest point on the graph. If it's not in vertex form, that's the second box, well, that's okay. There's a vertex formula. That's what the one we're about to use on our next couple of examples. The vertex formula says, if you have ax squared plus bx plus c, x coordinate is this way, take negative b over 2a. And for the y coordinate, we'll just take what your x value is and feed it back into the function. and you get your y coordinate in that way. And the best way to memorize all of this kind of stuff is that formula right there is a major workhorse, because getting something into vertex form without that formula does take some tricky algebra. And the way to memorize it is, it's also apparent here in the quadratic formula. If you memorize the quadratic formula, you get your vertex for free by peeling off the right stuff. Pretty much the square root goes away. But any questions about the vertex formula or otherwise? Okay, let's give this a try immediately. Here's our first problem that goes along with it. We have a quadratic function, its degree is 2. It's not an f of x, but it's just a matter of function notation or not. We always know that y is equal to f of x. First question they ask is, does a function have a minimum or a maximum value? We could throw this into Desmos and plot it, but there's a way to tell immediately. Any volunteers for what it should have, a min or a max? Absolutely. The way we can tell is the leading coefficient is a negative value. Let's first say that for our explanation on this. Since the leading coefficient, when we say leading coefficient, we mean the constant term that's associated with the highest power amongst all the terms in the polynomial. Highest power is 2, so leading coefficient is negative 13. I need a verb in there. Let me put is negative 13. Less than 0 immediately tells us, therefore, the parabola opens downward, giving a minimum. So essentially, it was that negative there, which tells us it must open downward. But again, we could just plot it to see what's happening. But it's good to know just by visual inspection how that should go. So we know we're expecting a minimum value. That negative 13 means, I don't know what the graph looks like exactly, but it's going to be essentially something like this. Part B is saying, where does the minimum or maximum value occur? Oh dear, didn't mean to scribble on it. That's meant to be eraser. What they're asking now for us is, well, pretty much the vertex. The vertex has 2 coordinates of where you're going to get either your minimum, or in this case, or our minimum in this case, actually. So we can say here, if it asks where, we're talking about the x coordinate. It'll be by formula, negative b divided by 2a. So we just go to our coefficients up here. The b coefficient is negative 18. So take negative of negative 18, divide by twice, negative 13. And that's where the minimum value is going to occur. It's only asking for the first coordinate, the x value. This will turn into positive 18 over 2 times negative 13. We can divide 2 into the 18 to get overall a negative answer of 9/13. So at exactly negative 9/13, we're expecting our minimum value. Yeah, go ahead. Oh, good question. It ought to be a maximum. I think we did draw this. Thanks for mentioning that and putting the brakes on this problem. We said giving a minimum, but I think the class did say maximum. I must have just wrote that in incorrectly as we got going on that. So let me put here, I'm gonna put this in red. If this was my problem on an exam, that'd be like a -2 on this. It should have been a maximum. Thanks for spotting that, Michael. Other questions or comments so far? Okay, so our graph should have a maximum value as it opens downward. So we're looking for a maximum, and at negative 9/13, well, it's not the maximum value, but it's the x coordinate you'd have to plug into the function to get that maximum value. So now we're going to find it on our part C. Any questions at the moment? Okay, so we can say our maximum value, that one's a y coordinate, and all we're going to do is take this right here, plug it inside the original parabola up above. Let's use maybe a slightly different color. It could go y equals negative 13. Then I'll plug in our negative 9/13 right here. We have to square it. Then minus 18 times negative 9/13. That one's to power 1, so then we'll just immediately add 23. So whatever that equates to, that's going to be our maximum value. Alex is kind of picky sometimes with these things. Sometimes they're completely fine with a decimal approximation. Sometimes they even request it. Other times they want the exact value. That's probably what we ought to do on this one, just in case that comes up on some of your work. So let's find the exact quantity for this right here. I mean, it's good practice dealing with fractions anyway. So think of this as just kind of different kind of math, a little bit relaxing, and we'll work through it. So first thing I'll do is square this quantity. It'll be negative 13 times 81. And I'll just call it a 13 squared down below, anticipating the cancellation of 13 into that 13. From here on out, we're going to need a calculator. So let's grab Desmos. We're going to take 18 by 9. So we'll get positive 162/13 plus, now in this next one, we're going for a denominator of 13. So I'm going to make this a 23/1 and multiply by 13/13 to get that least common denominator. Back to the calculator here then, across the numerator, we need 23 times 13. And we have a value of 299. So that turns into 299/13. So just about there. We can do a cancellation here. I'm going to cancel in this way that just says the exponent got canceled off. So this is just negative 81/13 plus 62/13 plus 299/13. So altogether, we have some quantity of 13ths. Back to the calculator. Lots of calculations today. It'll go following the red dot, minus 81 plus 162 plus 299. All of them take the same denominator, 13. So it'll be 380/13. So finally, that's our maximum value for that function. Well, we did it, folks. Yeah, go ahead.
The negative 13 have a difference, or like the negative important one.
This one right here.
Yeah.
It only was important in so much that when we go to put it in the calculator, we have to lead with negative there. Oh, gotcha. Other questions at the moment? Okay. When you do this kind of question in Alex, it's really not too bad. This is all we really did. Go to look at the vertex formula. You can even take a screenshot as a reminder. That's what we did on this problem. So applying the vertex formula, we first decided after some corrections there, thanks for the comments and corrections, because of the negative, it'll open downward, leading to a maximum. Then the location where the maximum occurs is negative 9/13. But that's just the x-coordinate of the vertex. The actual maximum value was this y value, 380/13. But that's this portion, the second coordinate of the vertex. And after going through all of this work, there's a nice thing about this. Before you shove your answers into, say, Alex and see if it's correct or not, definitely just plot the whole thing to see if it's lining up. You can put in first exactly how it's indicated, y equals negative 13x squared minus 18x plus 23. Then, as promised, it is opening downward. We have a maximum value, and our maximum should be 380/13. Let's see what that equates to. That should be about 29.230. Then if we click on the graph, let's see how close we got. 29.231. Looking at their expansion though, that would round to what we're getting. So that tells us we have extremely good numerical evidence that 380/13 is correct, which would mean that's also correct as well. If I made a mistake here, there is a very, very small chance, like a Powerball chance, of actually getting that figure right, making a first mistake. So it's nice to know there's always a nice check on these. But any questions, folks, on getting through this full process with vertex formula? Okay, so the vertex formula is a major powerhouse for these kinds of problems, finding maximum and minimum values. And that takes us to the last topic in section 5.1. There's some optimization style questions inside there. And this is the one I decided to bring to class today. There are several other versions, and if you're having troubles getting through them, let me know. I'm very happy to help out. I could post additional examples of whatever else they have in there just to show a template on how to solve each one of them. For me, it seems like this one's kind of the nastiest of the whole set, but think of example 7, the one we just got through. In a certain sense, it's really a warm-up to this. Once we get the function a of x, we're just going to try to maximize it, which means we're just going to throw the vertex formula at that whole thing and move on, just like we did on example number 7. First, let me scroll so we can see the whole thing. Here's the situation they gave to us. We have this wire right here in blue. The red is indicating that the length of that wire is 32 centimeters. Then the wire is to be cut into 2 pieces, each piece formed into the shape of a square. Who knows what's going on here, but here's our first square right here. There's a second square in that location. They say next, suppose that the side length in centimeters of one square is x as shown below. And that's all they tell us. So a wire has been bent, it's been cut. We have 2 squares that are being formed of at 32 centimeters. And we're told, find a function that gives total area a of x enclosed by the 2 squares. So that's our setup so far. It's tough to even start this, right? The best way to start this kind of problem is start throwing down formulas. They're talking about an area. Well, if they're talking about areas, we can say the area for this right here, that's just going to be x times x. So it'll be x squared here. This one's more confusing because they never gave us a variable. And we do need a second variable in the setup. So let's call it maybe variable y. Then the area of this second square will be area is length times width. Well, length and width are the same, so it's y times y for a y squared. So we've got a couple formulas down. We have an area formula. And because we're dealing with something that's 32 centimeters in length total, we also have 2 perimeters to worry about. Anyone see what the perimeter should be over here for x? Exactly. We just essentially are doing this. You could put x's all the way around the diagram if you like, add up all the lengths, but they're all the same because it's a square, and we get 4x. Likewise, for perimeter on this one, imagine y being the length on each 4 side, which it is if it's a square. Then the perimeter is the sum of the lengths, so 4y on this one. Well, we're getting there. Down below, I could write the area function right now, but we get stuck if we do that. Nonetheless, let's do it. It's total area, so a of x will be the area of the first square, that's just an x squared, plus the area of the second square, which is y squared. And I'll highlight this one because that's a problem. I can't actually work with the function as it stands. I can't use the vertex formula. I have nothing I can do with it because if it says area of x, I need to have exactly 1 variable on the right-hand side, yet we have 2. But if we can eliminate that y variable, we'll have a real function that we can work with, and we'll be well on our way on this problem. Now, going back to the drawing board on this, we put down an area formula, we put down a perimeter formula, but we still haven't even worked with this right here, the wire that was 32 centimeters long. So let's think of what's happening with this wire. There's a perimeter of 4x, and you can imagine if that first square is a little bit longer, it's going all the way up to maybe, say, here. I don't know where exactly until we determine what 4x is equal to. Let's say from here to about here is 4x. If we do that, we can use the same kind of argument. This perimeter of 4y, that's just going from here to here to here to here, but it can be visualized as this segment right here. So this will be 4y. And then finally, looking at this overall diagram, we can bring in a new equation. Let's call this 32 equals 4x plus 4y. All we're really saying here now is that the total length of 32 centimeters is equal to the sum of the broken up lengths. The 4x coming from that square and the 4y coming from that square. The nice thing about this formula is, well, if we're struggling with trying to figure out what to do with that y squared, no problem, because right here, we have a formula that we can solve for y exactly on. We could start off by saying, dividing the whole thing by 4, we'll get 8 equals x plus y. Subtract x from both sides, and 8 minus x would then be equal to y. So that's essentially our key now. If y is 8 minus x, right over here, having a change of heart on, well, we can leave it as is. We can now say a of x equals x squared plus, put a little blank where y squared was. It still has a power 2, so I should put that there. But we found a formula for y. Y must be equal to 8 minus x. So now we truly do have a nice formula for a. It involves only x's. It's not in a standard form. It's not in a vertex form. So the next thing we ought to do is expand everything and collect our like terms. That way we'll have a function we can do a little bit more work with on the next part B. To me, though, knowing to do this is absolutely kind of tricky. That's, to me, the hardest part of the problem. And you'll know you have to do that if you have a variable that just doesn't belong. So the y there was the major hint. We need to use this information to make that substitution. Well, any questions, folks, at all to this stage? Okay, let's start to expand this out then. We have x squared plus 8 minus x times 8 minus x. So we need to expand that out as well. It turns into x squared plus expansion over here. First distribute 8 through, you'll get 64 minus 8x. Then distribute your negative x through, we'll get negative 8x again, plus x squared. And on our last step, we can say a of x is finally, combining our like terms, we have 2x squares, negative 16x's, and a 64 altogether. So that's our area function. Well, now that we have this, we can start answering the follow-up questions. First, we want to find the side length x. That's going to minimize the total area. But that word right there should make us suspicious. Is there really a minimum? Here's how we can tell. Look at the value here. It's positive, so our parabola should be opening, would you say up or down? Exactly, ought to open upwards. So its graph, whatever it looks like, is about like that. And we're looking for the x-coordinate x. That's going to give us the side length to minimize the area. Then on part C, when they ask for what is the actual minimum area enclosed, they're asking for the y variable right here. So we are definitely on the right track. If I got a -2 here, I shouldn't even attempt part B. I know that there's something wrong. We need to backtrack to see why we have something that would lead to not a minimum, but a maximum if it was negative. Well, I think we're in great shape, folks. If we're happy here, next thing to write is x equals negative b over 2a. All we're using right here is the vertex formula. So plugging in our information, I'll put in a negative here. Our b coefficient is -16, so we have double negation. It's going to be 2 divided by a. Our a value is this one here, +2. That means we have 16/4, and the whole thing will turn into just a 4 for the x-coordinate. Well, does that look right to folks on getting that value 4 right here? Okay, so what they're saying is, if we're trying to minimize the area of the 2 squares that's shown here and here, well, you should take a side length of x equals 4 centimeters. That's going to give us the minimum is what the claim is. But they're asking us next, what is the minimum area closed by the squares? Well, there's a couple ways to do this. If you're thinking vertex formula, all you're really doing is taking your 4, plugging it into the total area function. It's going to give you the total area for any x in the domain. So I think that's probably the better way to do this kind of problem, although it is not the only solution. I'll write area of 4 equals, inside here, just plug a 4 for x, so it's twice 4 squared. My 16 times 4 plus 64. See what that turns into. 4 squared is 16, so this is twice 16. 4 times 16 is negative 64. Then plus 64 tells us the whole thing comes out as 32. And this would be units of centimeters squared, whereas x would have been units centimeters. Totally forgot to put in the unit on that one. So they're now telling us if you pick x equals 4 centimeters, then our total area between both squares should be 32 centimeters squared. One thing that happened on this problem, which is interesting though, if you set x to 4 centimeters like we see right here, then plugging it in there, it means y is 4 centimeters as well. We did all that work only to find out both of these squares had to actually be equal in order to maximize the area. So kind of silly in that sense, but it's really just practice on getting through the vertex formula. And setting up a function is really the hardest step, I'd say, on this kind of problem. Well, any last questions, folks, on getting through this one? Never. That would be pretty rude, I'd say. If this was going to be an exam problem, it's going to be directed. It'll have a lot more hints, and it's designed to kind of move us through. And also another reason this probably wouldn't be an exam problem was 5.1 was really about this kind of stuff right here. If we did an entire section that was only about doing these, then probably one of those problems is on exam. But if it's like a last example, mainly it was here just to help us get through the homework, where this is not really the main topic, but it's still good practice. But thanks for asking about that. Some of these exam questions, they just have to be shorter so we can do them in a reasonable amount of time. Other questions at the moment? Okay, well, let's save this off. And we got through it, folks. That's our section 5.1. That one was definitely a longer section. And it's even taken a while to save it. There it goes. But the good news is 5.2 is kind of a break after all of that. So here we're going to deal with specifically the so-called power functions. All a power function is a variable, say like x raised to any power whatsoever. The power could be 5, it could be square root of 2, could be negative 12. But if we have anything like that, then this is what we're dealing with if we're considering a power function. So a power function is a function that can be represented in this form. Here, our only requirement is that k and p be real numbers. And just as a reminder, k is also known as the coefficient in this situation. It would be the leading coefficient, but there's only one term, so that's kind of a weird thing to say for a power function. So different kinds of power functions, they could look like this, just for some fast examples. So first one, let's say f of x equals negative 3, x to the power 7. That would be definitely a power function. The negative 3 is the coefficient k, and the 7 would be the exponent p. But they get a little bit wilder than that. For example, you could have a function that goes like this. G of x equals x to the power of negative 3.1. That's weird. I mean, that's an odd looking exponent for one. But as long as it's a real number, negative 3.1 is definitely real, you definitely have a power function. And for a third example, if you wrote h of x equals 8 over the cube root of x power 2, that doesn't look like a power function at all. That looks like a totally different kind of situation, but it really is a power function. We can use some exponent laws to write this out as 8 over, first thing that happens is, if you're dealing with a cube root, that's really an exponent of 1/3. So it's starting to look like a power function. X squared goes in. Another exponent law says, if you have something to a power 2 raised to a power of 1/3, well, those exponents will multiply together. you'll get 2 times a third. So it will be x to the power of 2/3. Essentially, all that's happened is if you have power 2 here, but you're taking a cube root, you divide by that root you're taking. If it was a square root, it'd have been 2/2, so just 2x itself. But with the power 3, it becomes 2/3. And there's still one more exponent law we need. This can also be written as 8 times x to the power of -2/3. If you switch position of the base x from numerator to denominator, or even from denominator to numerator, all that happens is the exponent changes signs. So we do have a power function. The power is -2/3 right here. And the coefficient k would have just been the 8. Just a weird looking function. So sometimes the power function you're looking at is kind of hidden. Other times it's obvious. It's just written in the form that we're expecting. Any questions, folks, about definition for power function? Okay. The next thing about power functions are, it's not too hard to take a look at what the graph has to be. So this right here, end behavior of a power function, it may not be super useful on these notes. I mean, there'll be an ALEKS topic where it's helpful, but this is very useful in section 5.3. This is really what this table is going to be mainly all about. So I want to put down 4 particular examples of a power function, and we can use Desmos if we'd like to just get a feel for what these ought to look like. So let's start in Desmos before we run through this table. What I want to put in is just a generic power function. Let's go back to a normal scale here. So to start off, let's let our function be f of x equals 3x to the power of 2. So that's our very first power function. What's a good takeaway about this is the coefficient here is positive, so it's turning into a parabola that's opening upwards, and the power here is even. We change the power to say power 4. That's no longer a parabola, but it looks awful lot like one. It's more flat over here by 0, and it becomes more steep on the edges. But it's still going up to the left, rising to the left, still going up on the right-hand side, so rising to the right. The only way you can change it is make it go down by changing the k value, make your k negative. But in a certain sense, as long as these are even, they all look about the same. They just get steeper here or horizontal here and steeper out here. No matter if it's power 2, 8, maybe 12. If you put in an odd power, like maybe power 3, now you have something different. For a odd power function, to the left, it's falling, but to the right, it's rising. And it doesn't matter which power we put on there. Power 5 does the same, power 7, power 77. I mean, it's not even graphing it accurately. It's so flat out here. The only way we can change where these are fundamentally going is, once again, changing the sign of the coefficient. If I put a negative there, I'm reflecting across the x-axis, and it turns into that. So those are the kinds of things that we want to understand. And now you can think of this power or this table as being really just an overall cheat sheet to this. On one column, you're only considering when p is even. That means essentially the arrows are going in the same direction. And if k starts out positive, the graph is going to look something to this effect. Which means it's going to rise to the left. And well, I guess I don't want to highlight all of that. I'd be highlighting the whole table, but that's what this takeaway is telling us. It's rising to the left and rising to the right. So we're looking at just the end behavior, not what's happening in the middle, but what's happening on the far left and the far right. Does that make sense to folks on our first entry here? Awesome. Then if we redo this, on this graph, all I'm going to change is make the leading coefficients negative. It's fundamentally really the same kind of thing, but it's reflected across the x-axis. And so it takes on this shape. So because of this arrow, we'll say it falls to the left. Because of this arrow, we'll say it falls to the right. So I would say one big takeaway so far on this table is arrows go in the same direction when P is even. So if P is even, the arrows are either both going up or both going down. Well, let's try this again. Now we're going to change gears to when P is odd and do the same kind of thing. Recall, it's kind of hard to see because it's all up above. P is the power on this right here. The f of x equals k x to the power p. Let me put it down under here just to make that apparent. I think that will make the table feel like it has a little bit more sense to it. So here's the k value right here. And here's the p value. So all we're doing is plotting multiple instances of those. Now, if we make p become odd, but the coefficient is a positive one, the arrows go in different directions. They go like this time. This is very much like the y equals x cubed function, but it could be x power 7, x power 9, and so on. From here, we see it falls to the left, and from this arrow, it's rising to the right. So now this time the arrows are going in different directions, but that always happens if you're dealing with an odd exponent right here. So if it's even, arrows go the same way. Let's put down here, P is odd. Arrows go in opposite directions when P is odd. So we have our graph right here. Just one more to put on. Now on this final portion, all we're doing is making the leading coefficient negative. So take this and reflect it about the x-axis. And this is our next graph to consider. Finally, we see for going to the left, it's rising. It's just getting larger and larger without bound. And if we're going to the right, it's falling since it's getting lower and lower and lower on that graph, again, non-stopping without bound. So this is essentially our big cheat sheet. It's going to help us plot any function in section 5.3 because the end behavior of a polynomial, all we do is find its most dominating coefficient, the one with the highest power, the leading term, and whatever is happening on that leading term, we just look at this chart, and that's what's going to happen to the polynomial. Just for emphasis on that, let's take a look at, say, this polynomial. I'm going to put in 5x to the power 4, then put in negative 3x cubed plus 12x squared minus 5x plus 9. So this is just meant to be a very, very random looking polynomial. Kind of hard to actually see. Let's blow this up. But at the end of the day here, the thing that dominates is an even power term. That's our leading term there. So both of the arrows must be going upwards. Yeah, go ahead. That's what I was trying to do on this one. It just depends on what happens in the middle. And that's the thing that's kind of frustrating about this problem is it's only talking about the end behavior. Sure, if it's a power function like this, that specifies the whole thing. But if we want some weird behavior on the inside, we probably have to do something along these lines. Let's make it be x minus 3, x plus 4, x minus 2, x plus 7. Put in weird things inside there, and let's put in times 0.2. There we go. And we have some weird up and down patterns going on in this one. But notice, if we were to expand this, it'd be degree 1, 2, 3, 4. So the arrows are still going upwards. Throw another x in, overall it's going to be degree 5. And now I have an arrow going, it's really hard to see, down on the far left, an arrow going up on the far right, but no idea what happens in the middle. All this table is going to tell us is the arrows on the left and the right, the end behavior. We have to sort out what happens in the middle in section 5.3, but we're getting there. Other questions at the moment? Okay, so this table becomes essentially our big cheat sheet in getting through our upcoming problems. And the questions that we're going to be dealing with in this section finally introduce a generic polynomial function. If we say we have a polynomial of degree n, this is what it would look like. Rather kind of nasty because it's in its most generic form. The coefficients are an minus 1, an minus 2, and so on until we get to a2, a1, and a0. That's just a constant term. The leading coefficient is always going to be this number an that's tied together with the highest power term in the polynomial expression. We know what happens to this as a power function, then we know the end behavior of that entire polynomial, but unfortunately not what happens in the middle of that polynomial. So that's what polynomials ought to look like. And because this is such a, in all honesty, nasty looking definition for a mathematical object, it's good to do an exercise right away to see, are we looking at a polynomial or not? So that's the purpose of this table down below. I have several functions, looks like 4 of them altogether. And our goal is to decide, do we really have a polynomial function? If we do, we'll be able to state its degree and its leading coefficient. If not, we'll just leave these portions blank. So starting off with that function, how would you all feel about this one? Does it look like a polynomial? Awesome, I agree with everyone. What does a polynomial have to do? Well, it has to have a positive integer for its exponents. If this is a positive integer here, that should still stay a positive integer, and we get all the way to x power 1. So the moment you have negative exponents, that's a worry, and that's pretty much the main requirement there. So we'll say here, yes, it's a polynomial. And now here's a couple tricks that we can get into to satisfy the rest of the table. The degree is going to be 1, 2, 3, and 4. I claim it's degree 4 just by looking at the form of the function, but there's another way to do this. If you want to get the degree and eventually the leading coefficient, you could just expand the whole thing out. Should we give that a try? Okay, it's kind of a relaxing, just a purely mathematical problem. Let's see, I think we might be able to fit it right here. Let's see if we can expand it out and just give it a little bit of extra space, just for good measure. So we'll write that this is equal to, I'll distribute the 3x into the x plus 4 group, and we'll get 3x squared plus 12x. On the x minus 7 squared, I'll put the result here, and I'll put it in the margin temporarily. I'll delete this for the moment, after a moment. X minus 7 times x minus 7. Every time you expand this out, we'll distribute x through. We'll get x squared minus 7x. Distribute the negative 7 through, you'll get negative 7x plus 49. So really, there's a pretty big trick to expanding out x minus 7 squared. You first just square x. There it is. Then you will know you'll get a negative 7 times x twice every time you do this. So I'll take negative 7 times x and just hit it by times 2 to get a negative 14x. We're getting that from right here. And then square the negative 7 to get plus a 49. We've expanded it a little bit, but it still expands. We need to take this polynomial times this one and see where all the terms come out. And really the major reason to do this right here is it's going to be a selling point. If you can see what the degree is just from right here, you'll know you never actually had to do all this. It's really just practice and to help us see what the shortcut should look like. So let's keep on expanding. I'm going to take that 3x squared and distribute through all the terms on the right. We're going to get 3x power 4, then minus, let's see, 42 x cubed. And then finally over here, this will be plus, I think that's 147 x squared. Not the friendliest numbers, but we have calculators if we need them. So we'll see how we do on this next bit. Now distributing 12x through, we'll get plus 12x cubed. I'm running out of space, so I'll just drop it here under its like term column. Multiply 12 by 14. That's not something I have memorized. So let's consult the Oracle here for a moment. 12 times 14 is 168. So take 12x times that negative 14x, and we get negative 168 x squared. And even bigger numbers, geez, we need 12 by 49. That comes out as 588. So plus 588 x. Now we're almost there. This turns into 3x power 4 minus 30 x cubed. And oh geez, 147 minus 168. That sounds like a calculator job, unless someone has it. Let me throw it in here so we don't have to work too hard. I get to negative 21 on that figure, so minus 21x squared plus 588x. So finally, we fully expand this thing out, and we can say the degree is 4. But here's the shortcut. You could have gotten the degree by doing this. There's a power 2 here, and that is considered a power 1. A power 1. When you go to distribute this through, you should be getting power 4 altogether on this thing, just by visualizing it. Does that make sense to folks on how we can find that degree 4 just by visual inspection? Awesome. So think of this as an x times that x would be x squared. We'll get an x squared from this, so x squared times x squared will eventually emerge as a 3x power 4. Now, the next thing we can say is we could have got the leading coefficient without expanding any of this as well. The leading coefficient is 3x power 4. We see it right here, that 3x power 4 in expansion. But even if we didn't expand it, this is what I would have thought of it as. It's going to be this 3x, eventually times this x, eventually times that x power 4 will emerge as 3x power 4. And a bunch of other terms. Here's the other terms you definitely get. But 3x power 4 will absolutely emerge right here. So there's two methods to this kind of problem. Either expand out the whole thing, and that's good to know how to do anyways. That's good practice. But if you do this a lot and you decide you're just going to look at it and find the degree and the leading coefficient, that's always completely acceptable as well. So one down. That one was a polynomial. How about that g of x there? Would you say it's a polynomial or not a polynomial? Kind of tricky because that x is in a denominator, right? And we have resolved this issue before. For example, that was an x in the denominator. We did a bunch of weird exponent work, put it up above, and it was a power function because the power p is any real number. It never specified if it had to be positive or an integer and so on. Yes, go ahead, sorry. True. But we need to put a power on x itself. And that's kind of the issue with this one. It looks fine at the moment, but if we look at our form for a generic polynomial, x should always be in the numerator of every single one of those terms. And another requirement was n is a positive integer, which means all of your exponents had to be positive as well. So if we try to fix this function and put it into this general form where we see the red dot is, it would look like this: g of x equals 9x squared. That was no trouble here. Where that x is in the denominator, we can force it up into the numerator by writing negative 6 x powered negative 1, and then plus 8. That's the closest we can do to get it into this format right here. But then, right where that negative 1 occurs, we get to say no. It is not a polynomial only because of the negative exponent. A polynomial has to have only positive exponents for every variable x that occurs. Like on this one right here, all the exponents came out positive, but the moment you have something negative, it's just no longer a polynomial function. So that means The degree is completely non-applicable. I'll write NA to say not applicable. And the leading coefficient, it's not applicable as well. Well, any questions, folks, with that one there? Okay, kind of the takeaway of an example two is we're trying to see which ones of these functions are really polynomials by visual inspection. And it's just a way to get through this definition, which honestly, it's a pretty tough definition. There's a lot going on in there. But one thing that definition was communicating is no negative exponents like we saw in this one. And it gets even worse. Well, maybe. This one looks okay. The exponent here is positive, and this one's positive. So I would say yes, this one definitely is a polynomial function. We don't have to expand it. We don't have to do anything fancy to it. But the question is still tricky. Anyone see what the degree should be? Good call. This one is not in our standard form where the highest degree term came first. There was no requirement on that. So sometimes they're mixed up like in this case. Nonetheless, the degree is the highest positive integer exponent that would occur. So that was not so bad. If we want to know the leading coefficient, it's all of this right here. Oh, sorry. Leading coefficient is all of this right here. Coefficient means just the numerical parts, not the variable. So it'd be -17. And oh dear, that means I made a mistake on this one. Sorry about that, folks. When it says leading coefficient, really we're just talking about the 3 right there. Leading term would have been all of it, the 3x⁴ as well. Let me just make a quick note about that. The 3x⁴ is the leading term, not the leading coefficient. I mean, that's picky, right? If this was a quiz or an exam problem, I wouldn't be that picky, but Alex is. So we have to be careful here since Alex wouldn't accept an answer involving an x if they're wanting leading coefficient. But we're nearly done, folks. Just one last one to get through. How about that for that function uppercase F? Would you say yay, it's a polynomial, or nay, no good? Yeah, go ahead. It turns out it's not. So absolutely good call on this one. If you see anything that's a fraction, anything that's a decimal, anything that's an irrational number like pi²2, they're okay as actual exponents. But here it said n is any positive integer. So it has to be 1, 2, 3, 4, 5, and so on. If you get 1.5, that automatically disqualifies it. So this alone would tell us, no, it is not a polynomial. And everywhere we put no, I highlighted the problem with it. Yeah, go ahead. It would just be just some kind of function. You know, I think the better name for this actually, thanks for asking about that, would be f of x is a rational function. If we did some algebraic work, we could write it as a p of x function divided by a q of x function, which should be indicated as polynomials. And so we could change that up into a different kind of function, but it just doesn't qualify as an actual polynomial function itself. Other questions or comments about this one so far? Okay, well, we got through it, folks. That's how to tell if we have a polynomial or not. And getting the degree and the leading coefficient, it's really tough. If your function looks like this one, you could either expand it out or look at how we highlight these things to determine which is which. And that's a really fast way to get through that kind of problem. Yeah, go ahead.
So just for the back of my mind, as long as it is not a polynomial, it's safe to say there's no degrees of no leading coefficient, or are there times where that can be?
You could still say leading coefficient on some of these, but it was only asking for leading coefficients of things that were polynomials itself. Other questions so far? Okay, well, we're nearly done with these notes, actually, as strange as that seems. Again, this section is really kind of an organizational section before we go into section 5.3. The major takeaways are, we need to know what a polynomial actually looks like, what its degree is, and its leading coefficient. And we need to know the end behavior, so we'll be using this table a lot as well. But here's some other interesting kind of problems. So you'll see some of these that are in Alex. I stole this one directly for Alex from the screenshot. Here we're going back to the end behavior of our polynomial functions. It's giving us 3 different functions to work through, and we just have to decide what's going to happen on the far left, what's going to happen on the far right. And here's how we'd probably answer a question like this one. For that f of x function, you could just throw it into Desmos, but that's not a guarantee we have as an exam question. So instead, you can analyze it in this way. Our exponent here is even. That means both the arrows are going in the same direction. Our leading coefficient is negative. And so now the question is, if we have an even exponent for our leading term there, and the leading coefficient is negative, will the graph look essentially like this, or would it look like this? Exactly. Our graph is pretty much just this one. So if that's our graph, we can say from here and here, it's falling to the left and it's falling to the right. And where does that fall? Falls to the left, rises to the right. It would be this one right here. So this is an Alex topic where literally all you're doing is going back to the original table we built, this one up here, and just seeing which functions that were given actually corresponds to the right information. Again, what's kind of amazing is this is not a power function, but eventually when x gets really large or x gets really small, that's the only thing that controls whether the function is going to be increasing to the left or decreasing to the left and vice versa for the right. Oh, trying to erase that. So let's try this again. On this one, f of x equals 2x cubed. Well, the graph this time is either this one here or this one here. Anyone recall which one it should be? The first version or the second version? Exactly. If anytime you plot anything that looks like a cubic function, it would look like this. And because the leading coefficient is positive, we don't have to invert that across the x-axis. So our whole problem is really going to look like this situation. It's rising to the right and falling to the left. And so let's see here, rises to the right and falls to the left. I think that's this first option. So falls to the left is that portion, rises to the right is this arrow right here. We don't know what happens in the middle, so we're just drawing these generically, but we do know what happens in the end behavior at least. Well, any questions, folks, on getting through that one? Okay, C is the one where there's a couple options on the table for us. We can either expand the whole thing, not too bad on this one. Let's try the shortcut first and see how we feel about it. If you were to distribute all of this, we would get a leading term that would come out as, first it'd be negative x times a positive x times that's 5x right there. So negative x times 5x would give us negative 5x cubed altogether. So in our full expansion, there's more stuff, but that's going to be the leading term itself. Leading coefficient is negative, the power is odd. So this time it's going to look more like this. Almost like part B, but the whole thing is inverted because of that negative 5. We flipped it across the x-axis. So to the left, it's rising. To the right, it's falling. And let's see, where does that fall? Falls to the left, rises to the left and falls to the right. We'd be on this option right here. On the left, it's going up. So we have rises to the left. On the right, it's going down. So we have falls to the right. So we got it, folks. That's really kind of a freebie problem in Alex. It's really just using that table that we did at the top of the notes. But these are the things we have to analyze. Part C is the worst one here because we have to think of what is the actual leading term. Any questions at all, folks, on running through this one? Yeah, go ahead.
So where do you get the exponent whenever you factor that out?
That 3 right there, it would have been this x times this negative x times this x times that 5x there. But if we were to distribute it all out, f of x itself would have been, you could first just distribute negative x into that first group. We would get negative x squared plus 3x, forgot my x, let me put it in, multiplies 5x plus 2. Then when you FOIL this out, you get negative 5x cubed minus 2x squared plus 15x squared plus 6x. But still, it boils down to just that right there, the negative 5x cubed. So there's two ways to do it, to fully expand, or just imagine what would be your multiplications by x that comes up with your leading term there. Other questions or comments at the moment, folks? Okay, well, I don't think we completely got through the notes. We have one last topic, getting through this problem here. But, you know, that might be a good problem to come back to on next class as kind of a warm-up. So how about we end class right here today, and we'll finish these off on Thursday's class. That sound all right to folks? Awesome, glad to hear that. Usually people don't argue with that, but glad to hear it. Well, have a great day, folks. And if you have questions, I'll be available here and in the Math Center as well.